Let's now take a look at the rules for procedure definition and procedure call. These are very important instructions since they are the foundation of data abstraction, higher order program, layered program organization, encapsulation, object-oriented programming, abstract data type. All of the concepts on which our complex software systems are based and permit us to build this complexity comes from the procedure definition and procedure call. That's why we will look at them separately. The procedure definition and call semantics, let me very briefly go over it intuitively, and then I'll show you an example, and then I'll give you the formal definition. So the procedure definition, it has two parts. We create the contextual environment first, and then we store the pair of the procedure and the contextual environment in memory, binding it to the variable. Okay? The procedure call, it has two parts also, slightly more complicated. It starts by creating a new environment. So when we execute a procedure, it executes with its own new environment. And this environment is calculated and created each time we call the procedure. And this environment is created by combining two parts. First, we take the contextual environment, that's part of it, and to that we add new links, which consists of links from the formal arguments, those are the identifiers in the definition, to the actual argument values, the values at the call. Combined, this forms a new environment, and then we will execute the procedure with this new environment. Okay? So let me show you now an example to show you how this works. So here's a simple procedure, P. What P does is it calculates y is equal to x plus z, so x plus 1. So its output y will be x plus 1. Okay? Procedure P has one free identifier. This is z. Okay? When we execute P, we have to know the value of z. So z is part of the procedure's contextual environment. Okay? Now let's see how the call works. So here first we have defined P, and here in the second part we will call P. Notice what happens when we call P here. We have P of A, B. A is equal to 10 and B is unbound. This, what does it do? Well, the body of P is y is equal to x plus z. But what must it really do? B corresponds to y and A corresponds to x. So B corresponds to y. That means the y here corresponds to the variable B, and the A corresponds to x, and the z is the same as before. So y equal x plus z, what it must calculate is variable b equals variable a plus variable z. So somehow the instruction y equal x plus z must do this calculation, b equals a plus z. That means y has to correspond to b, x has to correspond to a, and z has to correspond to z. So you see, this is the environment with which the procedure calculates. This environment combining in green, which the formal arguments and the contextual environment, and in purple, violet here are the variables corresponding to the actual argument. So somehow we have to create this environment E index P, and that's where the complexity under the formal definition comes. So now let's go to the semantic rules. So I'll give first the semantic rule of the procedure definition. So here, first we have the semantic instruction. So this is the instruction with its environment E. The formal arguments of the instruction are these arguments. The free identifiers in S, assume they're Z1 to ZK. So the contextual environment of this procedure is E, the environment at the execution, restricted to Z1 through ZK, only keeping the identifiers z1 through zk. Okay, so once we know that, we will create in memory the binding to the variable x, which corresponds to identifier x, the procedure, and its contextual environment. Okay, this is the first semantic rule. This creates the procedure value in memory. Now let's take a look at the second semantic rule for the procedure call. So here on top we have the semantic instruction. So we have the procedure call. X corresponds to the procedure, the Y's are the arguments, and E is the environment. The first thing we do is we make sure that everything is right. So there's a number of conditions that we check to make sure that we're doing a correct procedure call. First, the activation condition. Remember, for the if statement, the conditional variable had to be bound to a value. It's the same here. E of x, which is the value corresponding to the procedure name, has to be bound. So if it's unbound, we cannot execute. We will suspend or wait. Okay? So if the activation condition is false, we don't execute yet. So this is for concurrency. We won't say more about that. The second condition is checked. If E of x is not a procedure, then we have an error. It has to be procedure. If E of x is the integer 42, we cannot call it like a procedure. And the third one, it has to check the number of arguments, which has to be equal to n. So if this is wrong, we also raise an error condition. So if all of these three conditions are passed, then we will do the actual call. And that's where we have the formal definition. So that's the second part. So we remember, again, we have this semantic instruction on the stack with the environment E. In this environment, we have the procedure definition. So E of x is the procedure definition in memory with its contextual environment and the definition of the procedure. When we know this, we will put the following on the stack. We will execute the body of the procedure, which is S. Okay. And the environment that we will execute it with is the contextual environment of the procedure, adjoined or added to the links between the formal arguments and the actual values. So we have, in this environment, we have from Z1 to Zn, and here we have E of Y1 to E of Yn. And that is the environment that we called E index P in the example before. Okay, so this seemingly complicated formal definition corresponds exactly to the example here. Okay, corresponds to this example. You notice why I explain it separately. This is probably the most complicated semantic rule that we're going to look at in this course, but it's also the most important one.